Have you ever noticed that it's harder to start pedaling your bicycle than it is to ride at a constant speed? Or wondered what causes your bicycle to move? Or thought about why it goes forward instead of backwards or sideways? Perhaps not, and you wouldn't be alone. It wasn't until the 17th century that Isaac Newton described the fundamental laws of motion, and we understood the answer to these three questions. What Newton recognized was that things tend to keep on doing what they are already doing. So when your bicycle is stopped, it stays stopped. And when it is going, it stays going. Objects in motion tend to stay in motion, and objects at rest tend to stay at rest. That's Newton's first law. Physicists call it the law of inertia, which is a fancy way of saying that moving objects don't spontaneously speed up, slow down, or change direction. It is this inertia that you must overcome to get your bicycle moving. Now you know that you have to overcome inertia to get your bicycle moving, but what is it that allows you to overcome it? Well, the answer is explained by Newton's second law. In mathematical terms, Newton's second law says that force is the product of mass times acceleration. To cause an object to accelerate or speed up, a force must be applied. The more force you apply, the quicker you accelerate. And the more mass your bicycle has, and the more mass you have too, the more force you have to use to accelerate at the same rate. This is why it would be really difficult to pedal a 10,000-pound bicycle. And it is this force, which is applied by your legs pushing down on the pedals, that allows you to overcome Newton's law of inertia. The harder you push down on the pedals, the bigger the force, and the quicker you accelerate. Now on to the final question. When you do get your bike moving, why does it go forward? According to Newton's third law, for every action there is an equal and opposite reaction. To understand this, think about what happens when you drop a bouncy ball. As the bouncy ball hits the floor, it causes a downward force on the floor. This is the action. The floor reacts by pushing on the ball with the same force, but in the opposite direction, upward, causing it to bounce back up to you. Together, the floor and the ball form what's called the action-reaction pair. When it comes to your bicycle, it is a little more complicated. As your bicycle wheels spin clockwise, the parts of each tire touching the ground push backwards against the earth. The actions. The ground pushes forward with the same force against each of your tires. The reactions. Since you have two bicycle tires, each one forms an action-reaction pair with the ground. And since the earth is really, really, really big compared to your bicycle, it barely moves from the force caused by your bicycle tires pushing backwards. But you are propelled forward.
Newton's first law of inertia states that an object stays in motion with the same speed and direction unless acted on by an external force. Normally, a car and its occupants move around at the same speed, but when an external force is applied to the car, in this case by the crash test block, the occupants continue to move forward at the same speed until a force is applied to them. This resistance to a change in motion is called inertia, and it applies even when the velocity is zero. It's this property that enables people to do things like this. The china on the table stays pretty much at rest, even when the tablecloth's pulled from under it. That's because there's not enough sideways frictional force to overcome the china's inertia and get it to move. Back to the crash test. Because they're not wearing seatbelts, inertia means the occupants of this car continue travelling forwards until the windscreen applies the force to stop them.
Let's look at the inertia here. You can see the vehicle coming forward, it's stopping, but the occupants carry on because there's nothing stopping them carry on. That's the basic Newton's law here. So you can see the occupants, because they're unrestrained, the driver has hit the steering wheel and the whole steering column is crushed around him. You can see he's partially ejected and will be severely injured. The poor passenger, even though he was in the back of the car, protected by the front seat, because he's not restrained, he goes through the front seat and he's gone through the windshield, and you can see his head still sticking out there.
Of course, in real life, you get a lot less time to regret not doing up your seatbelt. Newton's first law gives us the idea that in a car crash, things keep going until something stops them. First used in the 1950s, seatbelts provide an external force that counteracts the passenger's inertia, bringing them to a halt in a more controlled way. But they're just one of the ways car designers reduce the forces on the occupants in the event of a crash. And every car designer also needs to understand the principle behind Newton's second law of motion.
Sir Isaac Newton. He came up with 3 laws of motion. We've talked about some of these before in previous episodes, and we're going to talk about his second law of motion. Now, second law of motion states that the strength of a force is equal to the amount of mass involved multiplied by any acceleration applied to it. That sounds a little complicated, but I have a simple demonstration to show you how this works. I have 2 objects. One is red and one is yellow, and that's neither here nor there. But this one is heavier, and you're going to have to take my word for it. I've got something inside the red ball, which does make it a bit heavier, and there's nothing inside the yellow ball. So I have 2 different masses, a heavier one and a lighter one. And I draw your attention to our high-powered air cannons, which I have here on the stage. Now, what I'm going to do is I'm going to try and move these, accelerate these objects across the stage, using exactly the same amount of force. So I'm going to put one of our objects, the heavier one, here, and our lighter object here. The force is going to be exactly the same behind each object. So I'd ask you, which one do you think would go faster and farther? Again, the force is the same, but our objects have different masses. If we look at that second law of motion, it says the strength of a force is equal to the amount of mass involved multiplied by the acceleration. I don't want to give anything away, but let's actually try this. Now, I've done something a little risky here, which is I'm pointing them at Parnelli, who delivers our programs here, has graciously accepted the job of tester for this. I've loaded him up, and we're going to fire these directly at Parnelli, and he's going to see which one is going to travel faster and farther. You okay with this? You're good? Good, because your contract says you're allowed to do this. So we're going to arm our system. We're going to put in some air pressure, so there's enough that should be more than enough. And we're going to do a quick countdown and fire these at our brave volunteer and see which one is going to travel faster and farther. All right, we're going to go 3, 2, 1, and... Could you tell which one was going faster and farther?
I had my eyes closed.
I did notice that you had your eyes closed, but I can tell you without a doubt the yellow one, the lighter one, was going faster and farther. So, what did we have? The yellow one. The yellow one went faster and farther than the red one because, of course, it's lighter. It takes less force to move something that's lighter. Now, not only do we see this in rockets, you want to have a nice light rocket to go into space, you actually see this in everyday life. With the price of gas going up, you'll notice people are trading in their heavy trucks for lighter cars because it takes less force to move that lighter object. So again, something that we're going to be seeing a lot more of. If that price of fuel keeps increasing, we want to try and find a really efficient way of moving ourselves around. For the Express here at the H.R. MacMillan Space Center, I'm Cam Cronin. Thanks again.
There are 3 fundamental laws of motion, discovered by the English mathematician and scientist Sir Isaac Newton, all the way back in the 17th century. In this video, we will describe and apply Newton's third law of motion. The third law of motion states that for every action, there is an equal and opposite reaction. For example, the swimmer pushes against the pool wall with her feet and accelerates in the direction opposite to that of her push. The wall has exerted an equal and opposite force back on the swimmer. The forces are equal in magnitude or size, but opposite in direction. Forces always come in pairs, the action and reaction, and often is not clear where the second force is. Think about someone sitting on a chair. Most will spot the downward force of weight, but will not consider the force of the chair on the person. It's easier to see this reaction force if she sits on a trampoline instead. However, there are actually two pairs of forces acting here. The man's weight is balanced by the gravitational force he exerts on the Earth. He is prevented from falling towards the Earth's center because of the upward force from the trampoline or chair, which is balanced by the force he exerts on the chair. The forces are equal in magnitude or size, but opposite in direction. Or pushing a book at constant speed across a table. The force pushing the book acts towards the right. The force of friction opposes this and acts towards the left. The arrow vectors are equal in length because the magnitude of these forces are equal. There is another pair of horizontal forces acting here. The book is trying to drag the table as it is moved to the right, but the table is kept in place due to the opposing frictional force where the table legs touch the floor. We mustn't forget the pair of vertical forces acting here as well. The weight of the book on the table and the upward reaction force of the table on the book. Consider a rocket engine in outer space. Hot gases are expelled from the back. The rocket pushes against the hot gases, and the gases exert a force on the rocket, which causes it to accelerate. At liftoff, there is another pair of forces between the rocket and the Earth, as we saw before with the chair and the book. So there are now two forces on the rocket. If, as we hope, the force from the exhaust gases is greater than the force from the Earth, its weight, we will get liftoff. Many people are familiar with the fact that a rifle recoils when fired. This recoil is the result of the action-reaction force pairs. A gunpowder explosion creates hot gases that expand outward, allowing the rifle to push forward on the bullet. Consistent with Newton's third law of motion, the bullet pushes backwards upon the rifle. The acceleration of the recoiling rifle is A, greater than the acceleration of the bullet, B, smaller than the acceleration of the bullet, or C, the same size as the acceleration of the bullet. Pause the video while you work it out. The answer is B. The force on the rifle equals the force on the bullet. Yet, acceleration depends on both force and mass. The bullet has a greater acceleration due to the fact it has a smaller mass. Remember, acceleration and mass are inversely proportional. For more on acceleration, watch this video. And that's how Newton's third law can be applied.
Oh, you're here again. I guess you finished watching this video too, huh? Well, what are you trying to do? You trying to pass the STAR test or something? Your exit task for today. To receive your very own rocket and launcher, explain to your teacher how Newton's laws apply to real space shuttle launches. Not just the third law, that's the easy one. All three. Good luck and have a fantastic rest of your day. Oh, and there's a bonus brain pop at the end. I know some of you probably already seen it, but hey, every little bit helps. Bye-bye.
Thanks, Moby. Hey, Tim and Moby. Can you tell me about Isaac Newton's 3 laws? From Jerome. Well, Isaac Newton was a scientist who lived in the 17th century. We have a whole movie about him, so you should check it out. Anyway, Newton came up with the 3 laws of motion that can be used to explain how and why stuff moves. Well, yeah, these laws are still in use today, so I'd say he was pretty smart. Newton's first law states that an object in motion will stay in motion, and an object at rest will stay at rest unless an unbalanced force acts on it. You probably don't think about it this way, but when a car is moving, everything in it and on it is moving along at the same speed. If the car has to stop suddenly, the objects in and on the car will continue moving forward. Guess we should have tied those on tighter. An object's forward motion will continue until an unbalanced force acts in the opposite direction to stop it. So, our seatbelts provided the unbalanced force that stopped our bodies from moving forward, but those ropes didn't provide enough force to balance out the ski's forward motion. Why didn't it keep going? Well, in this case, the force acting on the rock was friction. Friction is the resistance caused by any two objects in contact, and it always acts in the opposite direction of the motion. Newton's second law says an object that has an unbalanced force acting on it will accelerate in the direction of that force. When you're just sitting there, two forces are acting on you all the time. Right now, gravity is pulling our mass toward the center of the Earth, and the upward normal force of the ground is pushing up against gravity. We could sit here all day and go nowhere because these two forces cancel out. This hill is a different story. At this angle, gravity and the normal force are not canceling each other out. Gravity wins, and we accelerate. The net force that's acting on us and making us accelerate is a combination of the normal force and gravity. Look, friction. Newton's third law is this: forces always occur in equal and opposite pairs. When I pushed that door, it pushed right back at me with equal force. The door was the one that moved because friction between my feet and the floor combined my mass with the building's mass. The door is on hinges, which decrease friction, so it accelerates open. Maybe if you took off your roller skates. Or not. Oops. Well, that's about it for Isaac Newton's laws of motion. I'm gonna get Moby an ice pack.